Hi everyone, welcome to the 11th in our series of marine tech webinars. My name is Chelsea, I work on the Oceansgate project for Plymouth City Council and I will be your host for this event. During this webinar you will only hear myself and our presenter speak. We will not be able to see or hear any delegates. After the presentation we will be holding a Q&A session. Please use the Q&A chat bar to ask any questions throughout the presentation. If you see any questions you'd also be interested in hearing the answer to, give it a like and this will send it to the top of the pile. This webinar is being recorded with the intention to be available to others on demand. Enjoy, and I will now hand you over to Brett, President of the Submergence Group.
Thanks, Chelsea. Good morning, and I guess I'm here today to tell you a little bit about our company here in Plymouth, MSubs Limited, and one of the projects that we're particularly proud of, the Mayflower autonomous ship. So without any ado, I'll just jump right into it. Hopefully everyone can see what we're looking at. So MSubs is part of Submergence Group, which is a US company, but it operates as an independent entity and it provides product as an export to Submergence Group and other places, particularly the United States, but we also work with the UK Navy. And we employ all sorts of people, every type of engineer you can imagine, all sorts of master fabricators, master machinists, welders, composites experts. And as it says, we work across almost every engineering discipline you can contemplate in a very tightly knit team. And we produce these looking submarines that are here for you to see that are called dry combat submersibles, and they go on to work in the US and also with the UK for very specific naval missions. As I said, we do just about everything. So we do, the top left is our assembly high bay, and then you can see some images of hatches and other precision machining that we do on site here in Plymouth. We're a fully certified ISO 9001 Det North Veritas GL licensed facility to make components for underwater vehicle systems, both manned and unmanned. And what you see in the bottom right corner is a team of design engineers and electronics experts and electricians and technicians all working together to build the internal components of the submarine that'll later get installed. And that's indicative of how we function as a company. Our engineering team works hand in glove with our fabricators, our technicians, our machinists, and also with our US side. So we rotate our engineering staff through operations in the field, and we rotate our operational field staff from the US through the engineering and assembly side. So we have a constant feedback loop about what our clients like, what they don't like, and how to develop the product as we go forward. That's one of the things we build. That's the submersible S351. It's the prototype for the dry combat submersible in the US, and that's over in Virginia somewhere, I think, right now on the coast doing various operations. It's about 30 tons, 12 people or so inside it, fits inside a shipping container, and it was launched here in Plymouth and did all its sea trials here a few years ago. And you've probably seen these things every so often turning up at Royal Marines Turnchapel Base and driving around the Sound. We also make extremely large, that's actually the category, extremely large unmanned underwater vehicles. And we make some smaller vehicles too, but we're one of the only producers in the world, actually of two in the world, that produce fully autonomous underwater vehicles of this scale. So this is 60 plus tons, about 24 meters long. And this particular one was used to be sort of a enemy submarine that they could test all sorts of countermeasures against without actually having to have a submarine. And they could do quite dangerous things that you wouldn't want to do with two submarines working in very close proximity. So this is one of several we've built over the past few years, and we're spinning up to build another 2 or 3, hopefully one like this for the UK Navy. And we have one in service actually now that we're developing with the Defense and Security Accelerator here in the UK, and that you'll see that driving around Plymouth Sound from time to time. And then, well, other than those sorts of things and what MSubs does, we also do the Mayflower autonomous ship in partnership with Promare, which is a nonprofit foundation in the United States that paid for the vessel. Marine AI, which is a spin out of MSubs, and it's focused on creating a cognitive artificial intelligence to drive vessels around so we can navigate without any people on board. And our principal technology partner in that is IBM and also NVIDIA. That's right here in Plymouth, working every day. And their flagship project, or so both MSubs, Marine AI, and IBM, is on the Mayflower autonomous ship. Now, most of you have probably seen that it launched recently. And sort of the genesis of the idea is to commemorate the 1620 sailing of the Mayflower from Plymouth to Plymouth in Massachusetts. And we came up with this idea in discussions with the city maybe 4 years ago in 2016, and it sort of evolved as a wider centerpiece for the city. Initially, I know there was talk about building a replica, but we wanted to build something that spoke to the next 400 years, but being inspired by the events of the past 400, and in particular the Mayflower itself, sort of the idea of jumping off into the unknown, into some new beginning. And I guess in that way, the Mayflower autonomous ship, which is fully unmanned and driven by an AI system, has the most in common with the Mayflower in that, just like the Pilgrims weren't sure they were going to make it, we're not sure we're going to make it either on our transatlantic voyages. But for us, it's about research and discovery and exploration, not just about ocean science, which we'll do, but whether or not it's even possible to do this kind of thing with an AI vessel, and how safe will it be, and how will it deal with weather, how will it deal with other hazards that it may encounter at sea. So it's a very interesting, broad research program. And just to give you a little background, it's sort of funny to sort of put these things side by side, but as most of you probably know, the original Mayflower crossed in approximately 60 days to carry pilgrims to the New World, and it was a single wooden hull with flat sails. We're going to cross the same amount of water in 12 days, although speed is not of the essence because no one's there. We can stay at sea almost indefinitely, and the boat doesn't get bored, and it doesn't get hurt or lonely. It's a robot, but a very smart one that can collect all manner of oceanographic and climatological data. And its goal ultimately is to further our understanding of the oceans and our climate, while sort of being in the vanguard of the development of new types of ways to do research at sea. In this case, fully autonomous. And by that, I mean, we don't have to have any connection to it. It can operate without any communication from shore, although it has a robust communication suite, multiple redundant systems. It's all fairly low bandwidth, as the system was designed from inception not to need to be talked to. So we'll just tell it, go to Plymouth, Massachusetts, and it will plot its own course. It will consider weather, it will consider the power on board and any other material condition of the ship, and go by itself. Hopefully, that's the goal anyway. And unlike the original, it's a bit different. It's smaller. It's about half the length, so it's 15 meters, and it's aluminum and composite trimaran. So we didn't use any wood that I know of in the building of the ship, but you never know. Sometimes it's useful, and there's a piece here and there, but I don't think so. And the course we'll take roughly is we'll leave Plymouth. We'll sail past the Isle of Scillies, out across the Mid-Atlantic Ridge, coming near the Titanic wreck site, although hoping not to see the Titanic. We won't know if we do because we'll be deep underwater, which is not our goal. And then making our first landfall in Provincetown, where the original Mayflower did, and then ultimately pulling into Plymouth, Massachusetts. And we'll spend a few months there doing some science in and around Cape Cod Bay, tracking great white sharks, looking at fish stock and fish migration, and then down to Washington, D.C. for a celebration, and then back across the Atlantic in July of next year, coming back to Plymouth, and then, from there, we don't know, onward and upward, perhaps up to Norway. And then in the summer of 22, we plan to be in Spitsbergen if the ice pack permits. And so the ship itself exists. It was built all aluminum, very robust, 5 mil thick aluminum plate. It was designed here with at MSubs and working with several naval architect firms, and it was a lovely architect down in Falmouth, naval architect Rachel Nichols-Lee did the ship design, and it came out beautifully, we think. But it was built in Gdansk in Poland, and then it was taken apart so that it could be shipped and trucked across Europe into England, down to Plymouth, where it was outfitted and assembled, and then launched on the 16th, as you see below, with the Plymouth hull in the background. Right now, the ship's up out of the water again, getting a coat of anti-fouling and finishing off some of the work we couldn't get done prior to the launch day. And as many of you would expect, we were hoping to depart on the 16th of September this year, but the pandemic got the best of us, as it did with many other people, and we've delayed now until April 21, and so we're in the process of sea trials and making sure she's fit for the voyage. And then I suppose the challenges that we face in doing this is important to talk about. The biggest single challenge is the ocean. That is ultimately what we're contending with. The whole ship is designed to have a high survivability, but it's a small boat on a big sea, and nobody's built a ship yet that the ocean couldn't have if it wished. And then from there, we sort of look at the full autonomy. So that's the AI side of it. How do we implement that? How do we keep it safe? How do we certify that it's safe so we don't create a hazard at sea? That's been an ongoing project that I'll talk a little more about for the past 4 to 5 years. And then fault tolerance. So there aren't many, but there are some single point failures on the ship. We're trying to design as many out as we can, but to be honest, I'm more worried about silly problems like a rudder jamming or picking up a rope in the prop than I am about the failure of the AI systems. The sort of complex machine automation on which the AI sits, and then the good mechanical, electrical, naval design that we've undertaken, we do quite a lot. So we're happy about that sort of thing. Not worried about the AI either, because if it fails, it will cascade down into sort of less functionality at machine automation level. But it's hard if your rudder's jammed to get anywhere fast, that's for sure. So those are the things that really worry me. We have good connectivity with it, but as I said earlier, the goal is not to have to talk to it at all. It'll tell us how it is, but it's possible that it could lose its antennas or that we could lose communication with it. We don't want it to just become flotsam out in the ocean. We want it to carry on safely, and so that's a big part of the autonomy. Again, how do we ensure that we're safe? And then sort of making all the hybrid propulsion that drives the ship work. So it's got diesel, solar, wind, and some sophisticated lithium batteries in it. All of that has to work together to reduce all the carbon emissions and make the ship as green as we possibly can. It's a complex system, but it's very, very green, even though we burn diesel, because to do the type of research we're going to do with the vessel, you'd have to have something 3, 4, 5 or more times the size, so it burns very little fuel. Its hull form is very, very efficient, and so it's we consider it quite a green vessel. And at the equator, there's enough solar that it could run indefinitely on its electric motor, so we'll only use diesel when we need to. And then so the other major areas of challenge, I guess, would be regulatory. So who will class and flag autonomous ships? So we've worked very closely now and had great support from Lloyd's Register and the UK Maritime Coast Guard Agency. They are creating a class of vessel called autonomous that will be registered as and flagged as a UK vessel. And then they're working very closely with us and Lloyd's Register to make sure that we run a comprehensive test program to satisfy them that the autonomy or the AI system is safe. The IMO, it's interesting. They have rules about keeping a watch, and I'm sure we'll have questions about that. Our AI will keep a better watch than any person could at night, in the daytime, in fog and inclement weather. It doesn't get tired, it doesn't get distracted. It's got greater dynamic range and resolution than the human eye. And if we built it right and trained it right, then it should perform better than a person. But again, that's part of the overarching research program, so it remains to be seen. And then as far as resistance goes, I didn't write all of these slides. We do have some bureaucratic resistance, although that's largely broken down. The people in industry that we deal with, the older people, the retired folks or the folks near retirement, tend to be much more proactive and happy and positive about this than the younger generation, which always surprises me. Issues about risk are a problem. So who owns the problem when there's a collision? And we don't think there will be, but it is not debatable that at some time in the future, a manned and an unmanned vessel will collide, or that many 1, 2, 3 or more unmanned vessels will collide. We have manned vessels colliding all the time, and we like to remind people that the rules we have to keep us safe weren't written down because we were immensely safe over millennia and we just decided to codify all our best practices that we had from inception. It's the opposite. We've been sort of unsafe for millennia, and the rules evolved over time with technology and the development of trade to facilitate an increasing margin of safety or increasing safety in the marine enterprise. But there is no zero risk scenario. Fortunately for us, it's a small vessel. It doesn't move that fast. We've got Guard Maritime Insurance on board who fully insured the vessel against general and third-party liability. And they're the first agency or insurance agency to do that because they see this as the future and want to lean into that risk. And again, we're testing, and hopefully we'll be able to convince the MCA that it's safe. As far as a threat to traditional employment goes, I think we'll be creating more jobs actually that are safer, that are higher paid, that are in the technology industry. And I would say that, you know, the goal of this is this sort of tech and Mayflower is not to put people out of work. It's not to take people off the sea. It's to drive down the cost of going to sea, and particularly for research, climatological research, so we can get more data that we convert into information and better target where we send those manned research assets, which are few and far between and very expensive. So what we had to do, and there's a link there which I can send on as well if you have time to copy it down, with a video about sort of how we envision the AI captain working for the Mayflower. If you have an opportunity, I'd encourage you to watch it, and I can send that out in the chat link as well. But one of the most important things you have to do is get data. So you have to train the machine learning systems to recognize the things that it might find at sea. So what we've done in Plymouth is build up a system over the last 4 years of cameras and radars and AIS and LiDAR all around Plymouth Sound and offshore on offshore installations as well, and collected millions and millions and millions and millions of images of all the things coming and going into the Sound and elsewhere, and then sort of curating them, tagging them, making notes about them, assigning categories to them in the metadata with those images and other data sets from like radar, AIS. We can impart sort of intent about how something identified will be operating, so how a sailboat might move or how a commercial bulk tanker might move. But there really weren't any of these libraries for us to use, of libraries of image data and other data. So we had to create all of it. We did. And working with IBM, once we had the base data set, we could auto-label new features and sort of retrain models and develop models very quickly. And a computer model is the thing that sits out on the edge on a tiny little computer that is connected to the camera, the radar, and helps identify what the things are around us and where they are, so that we know what to do to avoid them. And again, we have many different types of models. We have an uncategorized model, models about buoys, models about moorings, models about docks, models about boats, and many, many categories of ships, boats, rafts, canoes, paddle boarders. They were particularly hard to model because we hadn't thought that we might need to teach the computer how to recognize a person standing in the middle of the water for no apparent reason. So that was an odd one for us. We had to develop a model for paddle boarders. And all those models sit out on the machine on the Mayflower on little NVIDIA single board computers, and they process all the incoming data real time, determine what the things are, and then create sort of a cohesive sort of scene as to where everything is. And just to backtrack a little bit, we had these data collection points, most specifically at the end of Mountbatten Jetty and the breakwater fort, but then we had them all around the Sound collecting all this data. Sort of like a digital twin, although we haven't gone down that road, and it would be too long a discussion to get into here. But then once we have all that fused data, radar data, AIS data, sonar data, video data, or incoming video that we can process and tag the obstacles accordingly, we can then create a safe route map that tells us where all the obstacles are and what we think the safe course is, as illustrated below on the left. But to do that, it has to happen constantly. So we're dealing with many targets moving in many different ways. We have to take into account windage, current, weather in general, and we have to be able to navigate around it. Now, the nice thing about being close to shore is we have great communication with it, with 4 and 5G provided by Vodafone, and then Wi-Fi and other ways to talk to it, directional low bandwidth radio as well. And so we can sort of intervene if we need to, if we feel the models are breaking down, because the scene becomes too complex, which is possible for people as well as computer systems or AI systems. But when we get out in the deep blue, we won't have that level of communication. Fortunately, there shouldn't be as many things out there, and certainly a smaller category of things to worry about. Weather and sea state becomes more important. The number and type of ships you see will be greatly diminished than inshore. So we won't see jet skis, or hopefully we won't see swimmers. That would be strange. I'm sure they'd be happy to see the ship coming to them if they were swimming somewhere out over the mid-Atlantic ridge. So it aligns nicely that we have lower bandwidth further from shore, but there are fewer things that we have to contend with, or for the ship to contend with, in terms of plotting a safe course. And of course, we'll be learning about, you know, the depth, the conductivity, the fluorometry, all the weather data you can imagine. We'll be testing innumerable scientific payloads from Plymouth University, from Bristol, from Woods Hole, from Scripps out in California, and from many private companies that have provided equipment to help make the ship an unparalleled science platform as well. And so to go back to rules, so while we're doing that, I mentioned earlier the international regulations for preventing collisions at sea. We create all these models and sort of comprehensive scene, but then we have to produce sort of an output of a navigation hazard. We integrate all the data, and then we follow coal regs. But in order to follow coal regs, you sort of have to teach the ship that. And that's sort of one of the interesting things. We were able to work with IBM to bring across a piece of financial software called Operational Decision Manager that is used in the financial industry, and all of us have used it, we just don't know. So when you apply for a credit card or a mortgage, you do a foreign currency exchange, you move money from one bank account to another, you use your credit card at a restaurant, some version of ODM, which has been around for a long time and been constantly improving, looks at the rules against transactions you're engaged in and determines if they're appropriate. So is it the right person using the right PIN in the right place for an amount of money that they have, all those sorts of things that seem mundane, but all this is happening in the background of every transaction. And we found that we could take that operational decision manager out of the cloud and stand alone on the boat, deploy it on the Mayflower, and then we could teach it coal regs. So the rules for navigation were quite simple by comparison to, say, all the complex financial rules. But what it also does is it keeps an immutable text record in natural language of every decision it makes. So it looks at the whole scene that the probabilistic model or the mission manager has sent to it from the higher level AI. It looks at all the targets around it. It looks at the rules that apply, how everything is moving. And then it determines a set of actions, either change your speed, change your heading, so you can slow down, come to a different heading, or stop, whatever it may be. And then it sends those back to the mission manager saying, you can do any of the following things and remain compliant. But it keeps a record of all this. And then it also keeps a record of the actions that the mission manager takes or that it chooses from the available options. But at the end of the day, our policy is just don't hit anything, which seems like a good base policy. And we can update these rules as we go, as we learn. I'm sure there's some things we've missed, but that's why it's a research project. And then the nice thing is, what falls out of that also is sort of, and this is just a graphical representation of it, but you can see here in the bottom where the big yellow arrow is, it's telling you, you have one ship crossing, you have Mayflower moving in this way, and this is in a sim. And the decision manager is telling you what to do and why, and referencing the rule. This will be sort of critically important in the future if there are collisions, that we can sort of assess what actually happened, because we don't want AI in a black box and not understanding things it's telling it's, or parts of it are telling the other parts of it to implement. So Mayflower is sort of testing all this sort of bleeding edge stuff right here in Plymouth as well. But maybe I've banged on too much about it. I've sort of come to the end, back to this picture, which is the Mayflower autonomous ship, as you've seen earlier. And so she's here now in Plymouth, and you'll see her sailing around with our support boat, and it won't answer you if you call it on the radio. That's our next research project with NVIDIA, is a natural language processing system. So when it's out at sea, if you hail it, it will actually understand you're calling it and talk back to you. And ultimately, we'll do away with all the sort of text-based input that we can give it for control, and you'll just be able to speak to it literally and tell it what you want it to do. And we're still a few years off, but it's fun work anyway, trying to get to that point. And we hope most of what we develop so that on the IBM technology platform will be portable to manned and unmanned vessels alike to help aid in navigation and safety at sea. So that brings me to the end, and you can email Chelsea, and then she'll happily put you in touch with me if you have other questions. And I'll close out that presentation so I can see you guys and take questions.
Thank you, Brett. So if anyone has any questions, please use the Q&A chat bar. Brett, there is a 30-second delay between us and people watching, so we'll just give them a minute to write any questions down.
Okay. Well, I hope I didn't rush through it too much. There was a lot there, and
no, it's great. Thank you for that.
I never know what to talk about with these things. I do these quite often, so I'm never sure what people are interested in. I'm always surprised. I like the Q&A part the best. No questions. I dazzled them.
I always, it's just before I go to close it, there's always someone that just gets in there. I'll just give it one more minute.
Okay. I have all the time in the world, no worries. I never know where to look on these things, Chelsea. I feel like.
Well, I've seen that there's been a few sort of like professional programs where you can learn how to be professional on camera and stuff, and but I've not fancied it myself. But no. I think the general rule is you have to try and look at the camera, but it's just not natural because it's so much higher than.
Yep, and there's nobody there, exactly.
Yeah.
I would love to get back to normal as soon as we possibly can.
Yeah, same. Okay, there doesn't seem to be any questions coming through, so I will draw it to a close. If anyone does have any questions, please feel free to email me and I can always pass them on to Brett. Thanks. Everyone.
Bye.
Bye.